L1 is parallel to L2, then L2 is parallel to L3. Visually, it is clear. Then L1 is parallel to L3. Maintaining this condition, A minus B is even. You see, 2 minus 2, 0, that is even. 2 minus 4, minus 2, that is even. 4 minus 2 is also equal to 2. Therefore, all are maintaining this condition. Morning, welcome to btosacademy, welcome to my maths class. Today, in the first part, I shall work out few problems on relations. Then I shall move to the other important special type of relation, that is function. First of all, I have taken two sums on the board. I shall work out these first. A relation R is defined by this relation having ordered pairs XY, where XY are natural numbers and x plus 3y equal to 12. You have to find the domain range of the relation R and then R inverse relation. Given since an equation is given, first of all, from this equation we express y in terms of x or x in terms of y. Then, maintaining this condition, we find the order pairs. Follow. Now we make the table like this, keeping in mind that x, y are natural. First of all, we start by taking x equal to 1, then 12 minus 1 divided by 3, that is not integer as well as natural number. Next we take x equal to 2, then the result will be 10 by 3, not integral value. Then x equal to 3, x equal to 3 first. 12 minus 3, 9 divided by 3, that is also 3. Then for 4, 5, the value will be fraction. We reject those. Then x equal to 6. Then 9, 12 minus 9, 3 divided by 3, that is 1. Therefore, order pairs are 3, 3, 6, 2, 9, 1. We find these three ordered pairs satisfy this one, where x, y are natural numbers. Therefore, the relation R is equal to set of order pairs 3, 3, 6, 2, 9, 1. Students, I suggest follow the steps what I am doing. First of all, you read the problem, try to understand, then the equation is taken first. From that we have expressed y in terms of x. Actually, we have to find the order pairs. Those will be satisfied by this one condition. Then after getting the order pairs, we have written the relation this. Then domain of the relation, that means set of first components or set of first coordinates of the order pairs, also we call set of first entries of the order pairs. Here we find 3, 6, 1. I write in ascending order, then range of the relation, that means set of second components, domain 3 3, 6 3, 6, 9. Oh, I have written wrongly. 3, 6, 9. First of set of first components 3, 6, 9, and range set of second entries 3, 2, 1. I have written in order 1, 2, 3, ascending order. Therefore, we have found domain and range. Then inverse of this relation will be set of order pairs in which the components will be interchanged. That means R inverse will be components are interchanged. For the first order pair 3, 3, for the second one 2, 6, then for the third one 1, 9. Therefore, this sum is solved. Next we move to problem number 2. First I rub this one. A relation R on N is defined by this one. X minus y is divisible by 5. We have to show R is equivalence relation. Let us first remind a relation R is defined or called equivalence relation if R is reflexive, symmetric and transitive. I shall first show step by step. Divisible by 5, x, y are elements or members of set of naturals. R will be reflexive if x is related to itself, means xx belongs to R. x minus x is 0, which is divisible by 5. Therefore, x6 belongs to R for all x belongs to set of natural. Therefore, R is reflexive. Symmetricity. Let us first recall, if xy is member of R, then yx will be member of R, or xy, yx both belong to the relation R. X minus y is divisible by 5. Therefore, x minus y equal to say 5k. Divisible by 5 means x minus y is multiple of 5. Therefore, y minus x is equal to minus 5k. That means 5 into minus k. Therefore, 5 divides y minus x. In other words, y minus x is also divisible by 5. Therefore, as per definition, x y belongs to R, y x belongs to R. Therefore, R is symmetric. Thus, we have verified reflexivity and symmetricity. Then, transitivity. Let xy member of the relation R, yz another member of R, so that x minus y equal to say 5k1, y minus z equal to 5k2, where k1, k2 are natural numbers. Therefore, x minus y, if we add these two, therefore x minus z is divisible by 5. Therefore, xy member of R, yz member of R implies xz is also member of R. Therefore, R is transitive. Therefore, R is reflexive relation, R is symmetric relation, and R is transitive relation. Therefore, R is an equivalence relation. Follow the steps. X minus x, that means if we take difference of two equal numbers, value will be 0, and 0 is always divisible by non-zero number, therefore it is divisible by 5. Therefore, x belongs to R for all x belonging to set of naturals. Then we have found x minus, if x minus y is divisible by 5, that means 5 divides x minus 1. Then if we take the negative or negative of x minus y, that means y minus 6, that is also divisible by 5, so that R is symmetric. And in the last step we have shown if x y is an order pair or member of R, y z is another order pair of R, then x z is also a member of R. That means R is transitive. Therefore, the relation R is satisfying all these three: reflexivity, symmetricity, and transitivity. Therefore, R is an equivalence relation as per definition. I have taken two more problems. Let me solve first this one. L set of all lines in the xy plane given by this one, this condition, we have to show that is equivalence relation. First I write the relation in the xy plane, of course, as any straight line is considered to be parallel to itself. Therefore, L is related to L, that is order pair LL is member of R. Therefore, R is reflexive. We mention here on the xy plane. If L1 be parallel to L2, a straight line L1 is parallel to the straight line L2, then conversely straight line L2 is parallel to L1. Therefore, as per definition, if A is related to B and P is related to A, then we say the relation is symmetric. We find it here also. Therefore, R is symmetric. Thus, we have shown R is reflexive, then symmetric, then transitivity. If L1 is parallel to L2 and L2 is parallel to L3, we can show in diagram like this. L1 is parallel to L2, then L2 is parallel to L3. Visually, it is clear. Then L1 is parallel to L3. Then L1 is parallel to L3. Therefore, L1, L2 member of relation R, L2, L3 is also member of R. Therefore, L1, L3 is member of R. Therefore, R is transitive relation. Therefore, R is reflexive, symmetric, and transitive. Therefore, R is an equivalence relation. I think you have understood. Follow the steps I am following to show equivalence relation. We have to show step by step, first reflexive, then symmetric, then transitive. Follow this order. Now, if you find that any of these three does not hold, then the relation is not equivalence. If you see in the first step, it is violating, R is not reflexive, then without showing the other two, you make the conclusion that R is not equivalence relation. Actually, in case of less than relation, in case of numbers, that is not reflexive, because any number is not less than itself. Therefore, in the first step, the violation of reflexivity, then we can write or we can conclude that R is not equivalence relation. Therefore, problem 3 is solved. Before starting problem number 4, let me discuss this one. Find the set of all lines related to the line y equal to 2x plus 4. Since parallelism is the relation, therefore, last part, solution of 3, second part. Y is equal to 2x plus 4, which is straight line in the xy plane. Since relation is parallelism, therefore set of all lines which will be parallel to this straight lines parallel to line 1 are y is equal to 2x plus k. We know from the coordinate geometry that straight lines y equal to mx plus c and y equal to mx plus c1. That means constant are different. Then these straight lines are parallel. Hence, the straight lines parallel to line 1 will be y is equal to 2x plus k. Therefore, this sum, problem number 3 is finished. Then problem 4. Relation R in the set A having members 1, 2, 3, 4, 5 given by this. Absolute value of A minus B is given. Let us first write down the relation. A is equal to 1, 2, 3, 4, 5. R equal to set of order pairs AB such that A minus B is if therefore R is equal to, first we consider the least value, that is 1. Difference is even, therefore we have to consider 3, 5 with 1. That means order pairs will be 1, 3, 1, 5, 1, then 3, 1, 5, 1, also 1, 1. Then we consider 2, 2, 2, 2, 4, 4, 2. Then 3, 3, 3, 5, 5, 3, let me check. For 1, 1, 1, then 1, 3, difference will be even. Keeping that condition in mind, we are writing the ordered pairs. First 1, 3, then 1, 5, then the reverse is 3, 1, 5, 1, then we take 2, 2, 2, then 2, 4, here difference is 2, then 4, 2, then we consider 3, 3, 3, then 3, 5 and 5, 3. In all cases, the difference of the components of each will be 2. Now we have to check whether this relation is equivalence. Now 2, 2, 3, 3, 4, 4. Difference of 4 and 4 is 0, which is divisible by 2 or which is even. Here every member is related to itself because difference of 1 1 as well as 2 2 as well as 3 3 as well as 4 4 as well as 5 5 is 0, which is even. Now for all x belongs to A, you see 1 1 2 2 3 3 4 4 5 5 are members of R. Therefore R is reflexive. Next we consider first 1 3, then 3 1 is there, then 2 4 4 2, then 3 5 5 3, all are members of R. Therefore we can write like this: XY belongs to R for all XY belongs to A. Of course, those XY will obey this rule. Therefore, R is symmetric. Now let me discuss here. Then we have to check transitivity. One 3 member of R, 3 5 member of R, then 1 5 member of R. One 3 is member of R, then 3 5 member of R, then we see 5 1 is member of R. Therefore, conclusion is R is transitive. Therefore, R is reflexive, symmetric, and transitive. Therefore, R is an equivalence relation. Therefore, we have shown R, the relation R, set of ordered pairs A, B, maintaining this condition, modulus of A minus B is even, is an equivalence relation. This question has the second part, this one. We have to show all the elements of 1, 3, 5 are related to each other. First one. And take this one. I have taken this set as A1 and this set as A2. Now, as per this definition, each of all these order pairs obeys this condition: 1, 3, 3, 1, 1, 5, 5, 1, 3, 5, 5, 3. Difference of components is even. Also, difference of components of 1, 1, 3, 3, 3, 5. 1, 1, 3, 3. I have not written 5, 5. Is also even. Five, 3, 5, 1. Not. Each of the ordered pairs is obeying this condition, and from this what we find, all elements are related to each other. Therefore, all elements of A1 are related to and what we find, if we say relation 1 on A1, A1 also relation R1 on A1 is equivalence. Now, what is the explanation? We see AA, order pair AA, order pairs AA present in R1. Then AB, if I say this is AB, then B1 is, BA is present in case 1, 5, 5, 1, in case 3, 5, 5, 3, all are present in the relation R1. That means R1 is symmetric in that case, and we find 1 3 3 5, then 1 5. AB, BC, then AC is present in the relation R1. Therefore, R1 is also transitive. Therefore, the relation R1 is transitive. Therefore, R1 is a reflexive relation, symmetric relation, and transitive relation. Therefore, R1 is an equivalence relation on set A1. Similarly, we can show for A2. Order pairs will be 2 2, 2 4, 4 2. Maintaining this condition, A minus B is even. You see, 2 minus 2 0, that is even. 2 minus 4 minus 2, that is even. 4 minus 2 is also equal to 2. Therefore, all are maintaining this condition. Also, 4 4 is there, order pair. Thus, we see AA are present in the, if I call this relation as R2. Therefore, R2 is reflexive. Then 2 4 4 2 present in R2. Therefore, R2 is symmetric relation. Then 2 4 4 2 2 2 is there. We can say that R2 is transitive. Therefore, R2 is an equivalence relation. Also, if we make the conclusion, let us confine in this question all the elements of 2 4 are related to each other. All the elements of R2 are related to each other. Actually, transitivity is not clear in this case. Next, we have no element of 1 3 5 is related to 2 4. The solution is, if we take difference of 1 and any member of 2 4, the result is not even. 1 minus 2 or 2 minus 1 is not even. 1 minus 4 or 4 minus 1, difference is not multiple of 2. Therefore, no element of 1 3 5 is related to any element of 2 4. No element of A1 is related to any element of A2 as 1 minus 2 is not even. Therefore, we have solved this sum number 4. Already I have mentioned that I am going to start a special type of relation that is called mapping. First of all, students, you see I have drawn 3 figures. With the help of diagrams, I shall going to discuss function. First of all, function definition is that given two sets xy, both are non-empty, then ordered pairs xy, which is determined by some rule, formula, law, condition, any of these we can mention, so that every x, small x of course, of the set x is associated to some y in set y. In relation, what we have found that few members of set capital X is connected to or associated with few members or all members of set Y in ordinary relation. But in case of function, every member of X is to be associated with or connected to some Y of the set Y. As per that definition, we find for figure 1 the member x3 is not associated to any y of set y. Therefore, this is ordinary relation but not function. A function from set x to y is denoted by also we use this symbol X is called pre-image, Y image. Therefore, as per definition of function in figure 1, this relation is not a function. Now let us consider figure 2. Here we find two members x1, x2 of set X are associated to y1. That means more than one element of X is connected to an Y of set Y, and every X of set X is connected to some Y. Therefore, according to the definition of function, f1 is a function. But as more than one element is connected to an element of set Y, this is called many to one function. Many to one function. I shall discuss later. Now, in case of f2, here every x of set X is connected to a definite Y of Y. Therefore, here we see image of an element of set X is distinct. Therefore, in this case we say this is 1-1 mapping. And also other observation is that in f1, f2 both cases, members of the set Y, in this case y4 and in this case y4, y5, is not associated with any member of set X. In that case, we say into mapping. First of all, I define the function f. Let x, y be two non-empty sets, then the formula, law, condition, property, any of these terms is used, which connects every x of set X to a unique Y in set Y. Symbol for the function is taken in general f. Also phi, g, etc. symbols are used. I am taking here f. also called mapping. Formula, law, condition, property, if which connects every x in X to a unique Y, note the term unique, in Y, then F is called function. Now you see, uniqueness is maintained in these two cases, but not in this case. Therefore, this is not the case of function. And from this definition, it is clear that this is a special type of relation. When y is image of x, we express that by writing y equal to fx. Already I have written. And uniqueness is clear that x1, that is a member, is not associated to more than one y in set y. In this case, x1 is associated to 2y of y. Therefore, this is not the case of function. These two are cases of functions. When function from set x to y, that is given by this symbol y equal to fx. That means image of x is y. X is called pre-image of y and y is called image of x. From the discussion, it is clear that in some cases there will be y's in set y which are not associated with any member x of set x. Now, as per the definition of relation, here it is function, domain of x. Domain of F is the set X itself, and range of the function F is subset of Y. Y is called codomain as it is described in the relation. Now, I am going to discuss types of relations. Types of relations. Types of functions, sorry, not relations. Number 1, into function. If range of the function is proper subset of y, proper subset of y. You see, in both the cases, range this is the range of the function f. There is also range of the function f is proper subset of y. This can also be described as there is at least one y, small y of course, in y which is not associated with some x of x. In that case, we say the function is into function. Therefore, if range of the function f is proper subset of y, that is the codomain, then we say this is into function. Then 1 or injective function. Also called injection. That means every x, first I write this, every x will have, that means every p-image has distinct image. Note this case. x1 is related to y1, x2 is related to y2, x3 is related to y3. That means distinct pre-images as distinct images. This case is the case of 1-1 function or injective function or injection. And this is determined by two images are equal, then pre-images are equal. By using this, we show that the function f is 1-1 or injective function. Now, if we follow this diagram, we see there are two y's, y4 and y5. Those are not associated with any member x of set x. Now, if we consider this figure, so function 3 that means no y is there which is not associated to any x of set x. No element of y is not left out. Therefore, this is the case that is for every y in set y, we get some pre-image x in set x. Then we say this function is onto function, and the other name is surjective. Surjective function or surjection. The definition is the function f from set x to set y function f x to y if every y of set y, that is the codomain, is associated to some x in x, then this function is called surjective. Now the last one, bijective function or bijection. A function f x to y is bijective if f is 1 1 and onto. The simple meaning is that every x of set x is associated with distinct y of set y, and on the contrary, every y is associated with a distinct x in x. Follow this diagram, then it will be clear. That means if we consider the cardinal number of the two sets, then those will be equal. Therefore, we have discussed different types of functions from set x to set y.